Today we're going to hear from Lowell Kessel, who's a registered geologist here in the state of California, and he's with GEO, the Good Earth Keeping Organization company. He's a geologist and the director and principal geologist at GEO. He's been there 7 years, and he's got about 15 years in the field, the environmental cleanup field. Happy to host Lowell today. His talk is going to be about soil treatment using in situ gas thermal remediation and thermal conductive heating. With that, Lowell, I'll turn it over to you.
Thank you. So today's talk is going to focus on gas thermal remediation. We're going to look at two different projects in California. One was a dry cleaner site in the Bay Area, and the other one was a former MGP site in California, and that had benzoate, pyrene, TPH, and naphthalene. Of course, the dry cleaner had PCE, chlorinated solvents. But one of the questions that always comes up when you start thinking about remediation and you start your feasibility study for what remedial approach you consider, you think, well, is thermal remediation the right option? And really it depends on what the conditions are of the site. One of the things that we always emphasize strongly at GEO when we work with clients and collaborate on projects is a really good conceptual site model, really understanding where your source areas are, what the goals of the remediation are to be, if that's been negotiated with the regulatory agency for that site, and really understanding the geology, the contaminant, the distribution, the fate and transport, and having a good feel for what the challenges are going to be. Thermal is exceptionally well suited for challenging sites, and I think it's always been known for that. And some of those challenges is, from a practical standpoint, some of those physical challenges are when you need to have a very rapid source zone mass removal. Sometimes there's a complex mixture of COCs, contaminants of concern. That could be both L-naples and D-naples mixed together, or maybe there's pesticides and BAP and combinations of other things that really make any one single in situ solution rather difficult, and therefore you're considering maybe sequenced approach of different technologies. But thermal can, in a lot of cases, resolve that. Clay sites are always a challenge for any remedial approach, and for really developing a strong conceptual site model, mostly because it's difficult to really identify where sources are. If the contaminant is diffusion limited, and you've applied some pilot testing, maybe soil vapor extraction or some other approach, and you get a lot of rebound or very little reduction. So fractured bedrock is another very significant challenge, and those are the things that make thermal really well suited for. Those are the kinds of challenges that we like to see, and those are the projects that we look for when we work with our clients. From another practical standpoint is, what are the remediation goals? Rapid schedules, generally 3 to 4 months. We've done projects in 1 to 2 months, and it just kind of depends on what the property owner's goals are. Low cleanup levels and having a high probability of success are sometimes really important factors to drive the decision on which approach you're going to select. So some of the technical aspects of why thermal would be appropriate are, what are the benefits of heat? Vapor pressure will increase as you increase temperature by orders of magnitude. Viscosity decreases for those high boiling point compounds. Desorption will increase, and if you look at the diagram that I have on here, what you'll see is that as you add heat to a system, regardless of how and what form the contamination is present in the subsurface, and in most cases, if you've had some kind of release at some point and there may be some residual NAPL, you have all phases occurring and present at the site. And so there's an equilibrium established. And that equilibrium is different in terms of the concentrations or the amount of mass in any one phase, whether, considering whether you're in the source area or down gradient in the dissolved phase plume. So as you add heat, though, desorption will occur from the soil into soil gas, or if it's in the groundwater, it'll desorb and get into dissolve phase, into the pore space. And from there, it'll boil off and volatilize and end up in gas. So ultimately what happens is, whether you're heating NAPL up to volatilize immediately in the vadose zone, or you're desorbing it from the soil to get it into the vapor, it's going to end up in gas. And so with every thermal project, we have soil vapor extraction coincidentally operating so that we can remove any of the volatile and semi-volatile compounds that are present in the treatment area. So what are some of the other technical aspects? Well, thermal conductivity and diffusivity are important parameters to consider in thermal. Thermal conductivity is basically how quickly heat migrates through it, and diffusivity is how quickly the temperature of the material increases. And there's an equation there for you. And if you look at what does that mean in real terms, like for everybody, how do I apply that equation or those parameters? Well, let's look at the thermal conductivity of different geology: clay, sand, gravel, fractured bedrock, and in this case, this is an example of granite. You can see that the thermal conductivity of these different materials doesn't change very much. It could be by an order of 4, a factor of 4 maybe, at the extremes. So the difference between them isn't that significant. What that means is that as you go from clay to fractured bedrock, it's actually more conductive thermally, so heat will transfer pretty quickly. That's something that we model in all of our designs, and I'll show you some examples of some design models in just a second. But those are the kinds of things that really allow thermal conductive heating to be a very prominent option for a lot of remediation applications with a variety of different compounds of concern. So what about residual NAPL? Because really that's one of the big challenges for most in situ remedies that we've been using for a decade or a few decades in some of those cases, and all around the world. The problem is that if you have those clay sites or fractured bedrock sites and you haven't really been able to identify exactly where the source area is or residual NAPL pods are, that's going to be a long-term remedial program, and it's going to require a lot of monitoring and maybe continual applications or ongoing remediation just for that asymptotic drop. I mean, things are usually going to be within a year or two in the asymptotic phase, and it's flatlined. And what do you do? How do you get past that? That's probably begs the question: was the conceptual site model really detailed enough? But moving past that, and you look at this image that I have here, and hopefully from those here in the room and those online, you can see little air bubbles in this image. You can see there's a scale of 1 millimeter. So this is pore space, and this is where bubbles of water are boiling and turning into vapor, and then they start moving out of the system. Now heat transfer occurs at 10,000 times faster than aqueous diffusion in porous media rock, which means that basically it's going to be a very efficient way to remove mass. So what we did is created a little simulation, a cartoonish simulation, but hopefully the principles behind it are communicated effectively. So you have soil particles, soil mineral particles, you see micropore space, and what you see here, which look like vines or branches, those are preferential pathways in the soil matrix, and that generally always occurs. And there's always going to be some micropore space, and that would be macropore space. But there's always micropore space where water isn't moving regularly, and in those cases, that's where a lot of residual NAPO might reside. So how do you get to it when most of the flushing and volume exchanges are occurring where the macropore space is connected, and that becomes a real challenge. So as you start heating it up, the water starts to boil at 100 degrees Celsius, and so you can see some of the bubbles, vapor bubbles, boiling off. And as that occurs, it starts to remove and take some of the VOCs or contaminants of concern with it. And this is true even for high boiling point compounds that are very viscous, because once you get to 100 degrees Celsius, remember the viscosity has decreased, the solubility is increased, the vapor pressure is increased, and all of those benefits are in play to help make this contaminant more mobile and more easily extracted. So soil temperature profiles. What that was showing is that as you heat up the subsurface, you're seeing water start to boil right at this phase. And these are thermocouples. What you're looking at are thermocouples with temperature on the left-hand margin and time on the bottom. So you can see over time what a thermal zone heating up to superheated temperatures with a target temperature of 200 degrees Celsius. What's happening throughout the entire target treatment zone. And those thermocouples that are located in the Vado zone only can get to superheated temperatures rather quickly because they're not saturated. There's not a lot of water to boil off. There's always some water moisture, and that's what you see right here. But as you look at the thermocouples that are deeper and deeper into the saturated zone, those take longer to get above 100 degrees Celsius because you have to boil off the water. So for superheated temperatures for compounds like BAP and PAHs, those sorts that require high boiling points or have high boiling points and require higher temperatures, it's just going to take a little longer. And so you can see we're talking about a couple of weeks, sometimes a month, to boil off and get up to superheated temperatures. So now that we understand what the benefits are and how thermal works, let's talk about gas thermal remediation. What is it really? And basically, it's as simple as we use fuel, propane, natural gas, diesel, or any other type of fuel that's available to ignite a burner, and that burner is a gas flame that is about 700 degrees Celsius, and it moves down the center stainless steel pipe, which is encased in fully enclosed standard steel pipe, and so the hot air goes down, and then it comes up along the annulus, and then it leaves the heater well, and there's a combustion fan, and that basically pulls that hot air and emits it into the atmosphere. And this is not contaminants being emitted. This is just fuel. If it was a natural gas supply, it would be the same natural gas you use in your home to heat your house. And so that's it's basically a clean burn fuel, and from this system, the temperature on the edge of the steel, the outer steel, is roughly at about 400 degrees Celsius, and that's dictated by the temperature of the hot gas coming out. So at 400 degrees Celsius, heat starts radiating across the subsurface, and typically we have a number of these heater wells, and I'll show you some configurations in just a second. And so it'll radiate heat across this area and volatilize the COCs. And then you have a vapor extraction well to collect the VOCs. And that's as simple as it is. And then what we do is we just add multiple heater wells and multiple vapor extraction wells and voila, we have a complete thermal remediation system. Now, there's a lot of talk about, what are the ideal target temperatures? Well, there's currently consideration for low temperature heating down to about 50 degrees Celsius, which can be beneficial for biological activity. You can also use it for heat activated persulfate. If you only needed to heat up to treat trichloroethylene, you would only need to be at 70 to 75 degrees Celsius. But a lot of other compounds will require about 100 degrees Celsius. Unique about thermal conductive heating is that it's one of the what's the only thermal remediation option to get to superheated temperatures. And with our systems, we're able to offer both low temperature and high temperature. And because of the thermal conductive properties of different geological materials, it can be effective in bedrock, clay, silt, sands, and in saturated and unsaturated zones. And the most important thing, just to make sure everybody's super 100% clear on, it's a closed loop heating system. So there's no pollution emissions, nothing's being injected. We're just creating, we're making hot red steel to radiate heat in the subsurface. So another question is, since in situ thermal has been around for a while, mostly with the use of electricity as the main power supply, how is gas different? Well, from a thermal remediation perspective, it's no different at all if you consider thermal conductive heating. So our form of energy use is just a choice, just like you have choices to drive gasoline cars or electric cars, and and we have a lot of flexibility in the type of fuel. This has actually been very helpful for us internationally because in a lot of sites, it's very difficult to get power drops in remote locations, and the subsidized fuels in every country is different. So what's cheap here is not what's cheapest in other countries. And so we've learned through experience working internationally and across North America that flexibility is an important factor. In terms of if everything's converted to a kilowatt hour, just like in global warming, we convert everything to a greenhouse gas number or factor. You can see what the cost difference is between electricity and a couple of different fuel options. Now this is different. This is the national average as of April of this year. It's probably a little bit different now, and it's very different in every country. So something to consider in your own region and your own site, what the actual values are. So you can see what this is. What you're seeing here is the steel pipes. This is standard steel. This is the outer tube, and then this lighter looking is actually the inner tube, and that's stainless steel. And that's what gets superheated temperature. It's generally going to be somewhere in the 700 degrees Celsius range. So once it's installed, you can see that the inner tube is centered with a flange, and then there's an exhaust pipe coming out right at the side right here. Now I'm going to show you a couple of designs just so you can see what our design packages look like, and so you can get conceptually some ideas of what this configuration is. This is a plan view for a dry cleaner in Santa Barbara, and you can see we're actually inside the building. We have to enter through the front door in order to get everything in. You can see the carbon drums. This is both the vapor extraction well network as well as the heater wells. Each of the heater wells is just like in the cartoon. There's a PLC control and the burner just beneath it that's connected to the steel casing. This is another dry cleaner in the Bay Area. And so what we do is we create these 3D renderings that are actual designs down to the nut and bolt and washer and every other part. and we can visualize exactly what it's going to look like. And this is a very small footprint in a dry cleaner, another dry cleaner bounded by restaurants. And so working in small locations with, you know, adjacent to active businesses is not a problem. There's a lot of health and safety controls that go in that are part of the design of the system and the management. There's thermocouples all around the entire treatment system and within the treatment system in order for us to monitor performance and evaluate when we're going to hit target temperature. And that's important for us because we want to minimize the amount of energy we need to put into the system and make it the most cost-effective possible. So it's always a management process to make sure efficiency is always part of the program. This is a model of what the thermal profile would look like. And what's interesting here is that I'm showing you what the direct heater well temperature profile looks like. And generally it's, you know, just in the 400 degrees Celsius range, between 4 and 5. And then everything else is in the 200. And then there's these little tiny wells with actually the same diameter well, but it produces less heat because these are actually secondary heater wells. So for certain applications, such as vadozone applications, where we don't need to get to superheated temperatures, we will use the residual heat from the first heater well and pipe it right into the second one. And that allows us to be more energy conservative and allow us to heat a larger area with the same amount of fuel, essentially doubling. Well, not quite doubling, but pretty close. So this table shows 3 levels of thermal treatment. And as I mentioned before, gas allows us to operate our thermal heater wells at different temperatures, less than 100 and you know, definitely over 300 degrees Celsius. What you're noticing is that depending on the temperature, and which is really predicated on the contaminants of concern, the radius of influence will change on the heater wells. Well, that'll determine how many heater wells we're going to require. So generally speaking, the higher the temperature, the higher the target temperature, the closer spaced the heater wells are going to be, and therefore the more heater wells we're going to have. And that's there's a balance between efficiency and performance and cost, all in the design. And we actually have an iterative design process that evaluates what the optimal design would be. So gas thermal remediation is applicable in both small and large projects. I'm about to show you 2 case studies now that in more detail, in greater detail, to reflect that. And in short, basically, we can do small projects very quickly. Generally speaking, we can mobilize within 30 days of contract. It's scalable. We can do very small pilot tests at a very reasonable cost in order for proof of concept requirements. And then some of the small projects tend to be at a pretty reasonable price, and that would generally be dry cleaners. So you can see this is a dry cleaner, different from the other 2 models, designs that I showed. And this is the entire vapor treatment system on the right-hand side. And the heater wells are right here, and this is the PLC control box. And there's a separate PLC control for every heater, and every heater is managed individually and all part of a system. And that gives us a lot of flexibility, because if there's a groundwater flow in a particular direction that is a little bit faster than was predicted based on the conceptual site model of the client, that means there's going to be more heat loss on the upgradient side. So we have some flexibility by having individual controls for each heater well to manage or compensate for some of that heat loss and improve the heat, the energy, increase the energy flux in that area. So this is a site plan. You can see where the equipment was for the treatment area, and we actually used our cryogenic condensation system, basically a refrigerated condensation system that condenses the VOCs from the vapor stream. We used existing natural gas and existing electrical connection. There was on-site electrical treatment. And so you can see a closer view. We have 9 gas thermal heater wells, 6 vapor extraction points, and 4 thermocouples and pressure points. This is a chart showing the influent vapor concentrations going into the vapor treatment system, and you can see at startup over the next month to month and a half, we saw most of the mass being removed from the site through the vapor extraction wells and essentially flatlined, and while and during the heating process. And then you can see that certain SVE wells had higher mass removal rates than others, and those were just closer or within the hot points, the source areas. The end result was that we achieved 100 degrees Celsius temperature. That was the target in 185 days. Approximately 3,000 pounds of PCE and the degradation products, byproducts, were recovered as DNAPL with our refrigerated condensation system. So we can actually see in physical form how much of the NAPL was recovered. Post remediation vapor sampling results reveal decreasing concentrations, ultimately achieving low vapor intrusion risk criteria for closure. 825 pore volume exchanges are calculated to have occurred based on the condensate and removal rates, and almost 6,000 gallons of water was recovered. So our conclusion or summary from this one site is that, in particular, some sites have very strict limitations in terms of what you can get inside the building. In this case, it was a 3-foot wide door, and everything had to go through that door, and not, tearing down the building or going through construction permitting was not an option for the client. So sometimes that can add a little bit of complexity. High resolution site characterization is very key and could have probably been a little bit more precise. In this case, there was a little bit of the source area leaving or just outside the target treatment area that wasn't discovered, but it was determined during the treatment process that there was more mass there and coming from the boundary that was not part of the design. So sometimes that can high resolution site characterization or additional characterization can aid significantly in managing costs and expectations. And thermal can be used for vapor intrusion risk treatment criteria. So the second case study is a former MGP site. There was benzoate pyrene and a whole bunch of other related MGP contaminants of concern, including naphthalene, TPH, gas, diesel, and motor oil. Impacts from surface to 15 feet below ground surface, mostly sandy, gravelly soils, and there was no groundwater influence. It was pretty deep, so we weren't going that deep. You can see from the picture here what the site looked like. Each of these heater wells was independent. There was no secondary heater wells at this site as there was in the dry cleaner site, because the target treatment temperature is much higher in order to get these high boiling point compounds out of the ground. There was 15 vapor extraction points, 4 thermocouples, on-site liquid treatment, vapor condensation system with granular activated carbon vapor treatment. We used existing natural gas connection and existing electrical connection, so no outside utility upgrades were required for this project, actually for either project that I'm presenting on. This is the site plan view, so you can see what the configuration of the heater wells was. and you can see what the spacing was in feet, roughly about 6 foot spacing on the heater wells. And you can see the train of vapor treatment. It was a heater fan right here, which is pulling the combustion air out of the heater wells. Then you have a soil vapor extraction skid, chiller skid, and a second SVE skid before going to the carbon vessels. And then this is the water treatment system here. So after 60 days, you can see that the ambient temperature between heater wells was roughly in the 90 to 100 degrees Celsius range. And right around the heater wells were far in excess of 100, right around the 300 degrees Celsius. And then after 120 days, the ambient temperature was above 350 degrees. And at this point, once we achieve target temperature at any site, we have to maintain target temperature for a residence time, a certain period of time, to allow those contaminants to get out of the soil and into the extraction wells so we can get them out. And in some cases, we're using multi-phase extraction. If it's a high boiling point viscous material and there's a lot of non-volatile fraction component to it, we can actually flush hot water to get some of the NAPL out and do a combination. And we've done that at different sites. But in all cases, we're always, once we get to target temperature, we have to maintain target temperature for a certain period of time, depending on the contaminants. What you're seeing here are thermocouples and thermocouples over time. And we're looking at 60 and 120 day periods, similar to what I just showed in the plan view. And this is depth on the left-hand column. I'm sorry, the legend disappeared, but on the left-hand column is depth. And we typically always over-drill and heat below the target depth. So if the target depth was 15 feet for the bottom, then we will typically go 3 to 5 feet below the bottom, because there's a lot of heat loss at the bottom that we need to be able to manage. If you don't do that, then your bottom sample isn't really going to achieve the goals that's desirable. And that's true for all thermal. There is a lot of heat loss at the bottom, on the basically all the boundaries, bottom, sides, and at the top. At all sites, and I don't know if you noticed in one of the pictures, I'll show you maybe in a different picture, they always a concrete cap. And the concrete cap is to help provide insulation to minimize heat loss. So we put insulation on the surface, and then we put a concrete cap on top. And that allows us to walk on top safely. There's no safety hazards in the work area, and it also preserves a lot of the heat loss. And it makes the system more efficient. The results of the project showed that TPH motor oil was below the target treatment goal, and was essentially removed, as well as TPH diesel. The green is the pre-treatment concentration, and the yellow is post. And these are max. And so what you see is that there's no yellow on the TPH diesel motor oil. BAP was reduced significantly and to below the target treatment goals. And that BAP is benzoate pyrene, which was one of the primary contaminants. So when we look at how much mass was there, we did a mass calculation. Of course, mass calculations are always subject to error based on the quality and the how much information is available. But the calculation was that there was 1.47 pounds of benzoate pyrene, and post-treatment, the calculation using the same criteria and approach was 0.01 pounds. And there was no TPH identified post-treatment, removing 51 at least 51.43 pounds in 130 days. So some of the lessons learned from this case, from this project, was that there was more water content in the soil than expected. We really didn't expect a lot of water since it was just beta zone and groundwater was so deep. However, that does impact the heating schedule because you have to boil off all the water. So sometimes optimistic assumptions in the conceptual site model can sometimes lead to a slightly longer or a slight increase in expenses, and so that's something to consider. Electrical interruption caused a shutdown, and therefore when power goes out, there was a car accident and somebody hit a power pole, and so the power pole was providing, although we don't require a lot of electricity, we do have to have PLCs and computers operating to manage everything, and so when that shuts down and the SVE system shuts down, then that can cause a delay. So having backup generator is probably a good idea, or at least have something on standby. And this talks about heat loss at the surface. Thermal blankets. As you can see, there is some insulation placed on top, and we have for these really high temperature projects in excess of 300 degrees Celsius, we have a high R value insulation material that we use below concrete that helps to manage those thermal efficiencies. So in summary, the applicability for gas thermal remediation is quite broad, generally low temperature to high temperature. There isn't a lot of geological settings that we can't get to, although we currently have a limitation of about 100 feet in our thermal designs. We can mobilize rather quickly since our equipment's small, and most of the materials that we use, the vast majority, are common industrial materials and equipment. Scalabilities and flexibility is one of our strong points. We do really small projects as well as very large ones, and guarantees are available both on a time and spec as well as treatment goals. So I'll take questions now, and
what's the largest area you've treated?
Probably repeat the question for the webinar.
Yeah, the question was, what's the largest area that we've treated? And I'm going to say the project we're currently working on is probably one of the largest, and I don't know the exact number. I'll think about that and I'll get back to you. I'm trying to pull the number out of my head.
Less than an acre?
Oh, less than an acre. I think, yeah, it's definitely less than an acre. Although it's possible, it's just that any size is really possible. It's just a matter of how much gas supply and energy is going to be available there, and what's the need, what's the requirement. You can have a lot of people, checking equipment, and the burners will operate in sequence or simultaneously. For really large designs that we've done that we haven't started yet, we try to manage the site over a period of time so that we can do, also for capital reasons. If it's a really large site, tends to be in the tens of millions of dollars, and you can phase it, and that reduces the stress on the local community power requirements and gas supply. And so that's really the main consideration. Although from a physical standpoint, or implementability, we can do any size, but there's always some constraints local to the site that requires more of a phased approach.
Are there any situations where it would not be appropriate? Say you have a fuel spill site that's got a lot of methane, would that be contraindicated for this technology?
All right, so the question was, are there any sites that are maybe not applicable, then such as a fuel site that has methane? Um, um, methane will be removed from the subsurface really quickly. The question is, how do you manage the methane on the vapor extraction side?
Yeah, it will be removed quickly, but
right.
Not too quickly. Not too quickly.
Safely.
Yeah, exactly. How quick do you want it out? But the challenge is more on the vapor treatment side. If vapor treatment is required, then that will have to be considered as part of the remedial design. It doesn't present an issue for thermal or for gas thermal in that case if there's fuel, because we use it at thermal sites already. Our system actually has the ability to, just like a thermal oxidizer, to plumb from the vapor extraction wells directly into the burner units. And in that case, methane could be consumed as part of the energy. Yeah, we could use the fuel and methane as a fuel source to supplement what we're purchasing, from natural gas or propane or whatever it happens to be. That is an option, although it's not very efficient process. It doesn't consume a lot. More of it, the vast majority of that contamination will come out of the vapor treatment system. So, but it is possible that we can offset some of our energy costs with that. But it's not necessarily 100% of the contamination going through the burner. So it's a little bit different. However, in those designs, we can have the vapor extraction run next to the heater wells, and so there's thermal oxidation and taking place on its exit out. Because once it gets close to 400 degrees Celsius, it auto ignites and it's burning on the way out. So but there's some safety, factors that need to go into the design to manage that.
Mass removal is really important, obviously, but we're often driven by low cleanup levels for residential reuse, that kind of thing. And so mixing technologies is often encouraged as well. So do you have experience matching or mixing in a treatment train your technology with others? Even something like monitored natural attenuation? Yes.
So combining these approaches with thermals is actually really common these days. And some of the sites that we are working on are doing that now. And they're, one in particular that I can think of is using a combination of zero-valent iron and bio, down gradient of where the thermal treatment is taking place. And there's been a lot of papers and presentations at conferences documenting this kind of activity and this kind of work. And usually within the thermal treatment zone, you may need to, more than likely will need to bio-augment if it's a chlorinated solvent site. And I'm not really sure about the petroleum. There are specific bacteria that are that prefer petroleum, mesothermic and thermophilic bacteria, which are more well understood. I think there's current research right now about heat and chlorinated solvent degrading bacteria, and are there any other ones other than Dihalococoides that can take things down to ethane? So I think there's still a lot to be learned about that.
Would you say your remedy is used in conjunction and combination with other technologies more often than not?
Yes. Yeah, so I think any thermal really could be used in combination with other technologies.
It's not a silver bullet.
It's ours is not unique in that respect.
Right.
Really, the only uniqueness for us is that we use gas instead of electricity. and for thermal conductive heating that we can get to higher temperatures. With regards to heat activated persulfate for chemical oxidation, that's a possibility, although not commonly done. Heat does help proliferate bacteria in the down gradient portion on the boundary where it actually is influenced by the heat. So it's not really counterproductive. What we have done recently, even in the Bay Area, is at Hunter's Point, is to use hot water, and we will use the residual heat from the system to heat water that's on tanks, and we run the lines along the heater wells, and we use that residual heat to heat the water up to about 60 degrees Celsius, and then we inject that to flush the napple out. So we're combining hot water flushing with heat, thermal conductive heating, in order to help remove a lot of the mixtures of oils and sludge that are in the subsurface. So that's an option. Right now we're doing a design for doing the same thing, combining surfactants, and that's a little novel for the thermal community.
It's pretty similar to electrical resistance heating, except it looks like you maybe can get higher temperatures with this. Is that the case? And I was wondering about the spacing for your probes versus electrical resistance heating.
Okay, so your question was what's the difference between gas thermal and electrical resistance heating? Both in temperature and in well spacing. So in cost. Oh, I'm not sure I can comment on their costs, but with regards to temperature, well, we can get to 400 degrees Celsius, whereas electrical resistance heating is limited by the conductivity of water, which means you cannot get above the boiling point of water. So you can only ever get to 100 degrees Celsius, which is fine for gasoline and chlorinated solvents and certain semi-volatiles where you're just focused on a mass reduction, not a specific concentration. For high boiling point compounds like PAHs and BAP, if you're really going after a specific target concentration, you're really going to have to get to higher temperatures. And that's where thermal conductive heating is really the only option at that point. With regards to spacing, I believe electrical resistance heating allows wider spacing in general. It's like a generalization, but generally they have wider spacing of the heater wells than we do with the gas thermal remediation. In terms of cost, I don't know that there's a significant difference in the costs on the overall project for large projects, because at a certain point, the bigger the project, the smaller the difference the thermal provider makes, because drilling tends to be 20 to 30% of the total cost. The water and vapor treatment system tends to be another 10 to 15, maybe 20%. Energy tends to be 10 to 20%. Ours tends to be 10 to 15. I think for electrical, it's sometimes maybe a little bit more. But for small projects, I think we're very cost effective because we don't require a lot of big equipment and we don't require utility installation. So from a cost perspective, I'm fairly confident that we can do really small projects very cost effectively, comparatively.
Fractured bedrock. I mean, which technology would be more appropriate for fractured bedrock?
Okay, so the next question was which thermal option would be most appropriate for fractured bedrock? Electrical resistance heating is also limited by resistivity, and if the bedrock has a resistivity of about 500 ohms or greater, which is fairly common, it won't be able to conduct and heat in that area. You would really need a pervasively fractured, saturated, fractured bedrock zone in order for the conductance to get through it. But in a lot of cases, that's not going to be possible. It just kind of depends. It's something you would have to. The recommendation from all thermal providers is just to know where you stand. If the target temperature is 100 degrees Celsius or less, then you can choose any of the options. The next step, if it's fractured bedrock, is to collect the core sample, or 2 or 3 from different areas or different depths, and have resistivity tests done. And then that'll determine whether it's going to be viable or not. And there's a number of, we have our own lab, but there are a number of independent facilities, geotech labs that can also do resistivity testing and thermal remediation bench studies. Very good questions.
We have 5 or 10 minutes left. Why don't you see if there's any questions online and try to.
All right. For those of you that are on the webinar connected, do you have any questions that we can answer?
You have to type them in, right?
Yes. Okay. I'm seeing some questions here. Let me pull this out and open it up here. Looks like we got a good number of questions. All right. First question from Tom. Why don't you send the hot air down the outer tube rather than the inner tube? Well, the reason is that the flame and the burner unit is located in the center, and it's just easier to control this way. Otherwise, you have to have internal plumbing. That's a design question that was thought of and I guess figured a long time ago. Gas thermal actually started about 20 years ago for ex situ applications, and the designs have been many, but what we use is what is the most successful at this time. And as far as I know, the only commercially available option. Okay, next question. Renato asks, do you have a case where groundwater restoration is also a remediation goal? Yes. Typically, a lot of sites have a soil and groundwater remediation goals that need to be addressed, and that is part of the entire treatment design. What we ask for is the conceptual site model to really understand what is influencing the contaminant distribution, both in the absorbed and dissolved phase, and then we ask what the treatment goals are for vapor, for soil, and for groundwater. And based on that, we will design a thermal approach to address those concerns if it's possible, or we will address only the concerns where we are confident it can be the goals can be obtained. Next question. Philip asks, will it be possible to get a copy of this presentation? Yes. In fact, we're recording it, and once somebody who knows a lot about editing can make it sound better, it'll be redubbed and made available. So anybody who's registered will get the option of both downloading a PDF copy of all the slides as well as reviewing the recorded webinar. Next question. Please describe pros and cons of thermal treatment for creosote. And that was from Anne. I'm not sure what is meant by the pros and cons of thermal treatment for creosote. Creosote's a high boiling point contaminant. It's going to require in excess of 300 degrees Celsius to get a lot of it out. The question is, do you need to get all of it down to a very low level concentration, and what specific compounds does that need to be? It's possible to remove all of the volatile and semi-volatile fractions quite easily. And if it's in the Vado zone, however, if it's in the saturated zone and you have a lot of groundwater flow, that could be challenging and potentially cost prohibitive just in terms of heat loss. So creosote is a contaminant that requires careful consideration and a very detailed conceptual site model to have a proper design with the treatment goals in mind. And that's something that is never the same on any site, and it's always a case-by-case basis. So I apologize, that's not the answer maybe you were looking for. But give us a call and we can talk about it. Next question, what do you use to grout the well casings in, and how do you remove them? So the diameter of the boreholes is 6 inches, and the casings are about 5 inches, so there's not a lot of space. We use grout and high temperature grout or standard grout, and if that's a high temperature grout if it's available, otherwise standard grout, and then we cap it with insulation material and concrete. And typically removing them, we use a hydraulic jack to get it loose, and then it just pulls right out. Also depends on the length. If it's a shallow application, it's very easy to pull the steel pipe out, but if it's a deep application, it may not be possible, and sometimes they're abandoned in place. For really high temperature applications, sometimes the steel degrades and will become brittle, and then you start pulling a deep well from a site that had been heated to 400 degrees Celsius. It might just crack and break, and then you have to basically abandon in place with cement or whatever the appropriate abandonment procedures are for the state or the county that you're located. Okay, next question. Nick, how long do you typically wait before collecting soil and groundwater conformation samples? That's a good question. We typically like to sample immediately while the ground is hot. We call it hot sampling. And that's typically done about a week after we turn the heating off and before we demobilize. The reason is that we want to have the option to turn it back on if the treatment goals haven't been achieved for some reason. And there are specific procedures for how to do hot sampling, and that's not a problem. But it's a very good question. And it's a little bit trickier for high temperature sites. If the temperature of the ambient area is 300 to 400 degrees Celsius, it's going to take a lot longer than a week to cool down. And in that case, it has to be done differently. You might have to wait a little longer and also apply different techniques and maybe even use some cooling methods with water for the actual sampling area. But that's something that is determined on a case-by-case basis with the clients and the regulatory agency involved. How much more time do we have?
Maybe 3 or 4 minutes.
Okay, a few more minutes. Okay, next question is from Roger. First part, would this work on PCPs or PCBs and associated with TPH? Yes. And how would thermal remediation work in a small area around a lot of existing infrastructure? Well, infrastructure can be a problem if it needs to be maintained. If the integrity of the infrastructure is important and it can't be rerouted or abandoned, that could present some challenges. We have ways to manage that, such as injecting hot water over the utility corridor or in and around the utilities to make sure that the temperature doesn't exceed 60 or 70 degrees Celsius. That'll help protect, kind of like a warm water insulation. That allows flushing to take place right around the utilities, so you're still able to do some treatment there. And then we continue with the thermal conductive heating everywhere else. It just kind of depends on how pervasive the utilities are and where they are. Next question is, can it be used for PAH and TPH contaminants? Oh, as a supplemental fuel. PAHs, no. that's going to be a problem, because then now you have emissions that you have to be considerate of. The use of reburn, basically extracting contaminants out of the ground, has to be fuel. Has to be a gasoline, a diesel, and or maybe methane's there, but it has to be a clean fuel. Otherwise, we're now in the realm of oxidation systems, and that requires different kinds of permitting and vapor treatment. So, generally speaking, if there's anything other than a clean fuel or methane, then probably not going to have that as an option, and a standard vapor treatment will be required. I'll take one more question. How effective is the use of hot water to remove NAPL? Simple answer is very effective, because the hot water will reduce the viscosity and increase the solubility, and allow the NAPL to come out in liquid phase. And there are a lot of other questions that I'm not going to have time to, but what I promise to do is to get back to each of you who I could not answer questions for separately at another time.
So those are captured in the system?
Yeah.
Great.
All right. Well, thank you, everyone, and thank you for joining in on the webinar, and thank you, Mike, for allowing me to come to the office.
Thank you, Lowell. I appreciate your time, and thank the audience both here and out on the webinar. So with that, we'll sign off. Thanks a lot, Lowell.
Thank you.